Hello everyone, I'm happy here to introduce our work which has been accepted by CVPR 2024 as highlight, Vanishing-Point-Guided Video Semantic Segmentation of Driving Scenes. First, let's have a look at a photo taken in the nighttime in Zurich. And what is this? Let's drive closer. As we drive closer, the target becomes larger and larger. Now we can see clearly that it's a traffic sign. So the problem is, in autonomous driving scenarios, unnoticeable foreground objects in the distance often become difficult to recognize in unfavorable scenarios such as rainy days, snowy days, and night times. The red point, which exactly indicates the infinite distance in the image, is called the vanishing point. The region around the vanishing point contains more distant objects, which appear at smaller scales. Let's have a look at another example. Typically, the driving direction coincides with the direction of the vanishing point, which implies that most objects move radially away from the vanishing point as time progresses in the video. Based on these two priorities, here we illustrate the intuition behind our proposed vanishing point guided motion estimation and scale adaptive partition modules. Targets move radially away from the vanishing point as time progresses in the video. For the typical case of a forward-facing camera, a straight road, and linear forward motion, which is depicted in this example. Moreover, the region around the vanishing point contains more distant objects, which appear at smaller scales and are harder to recognize. Now we introduce the two modules that utilize exactly this pair of static and dynamic vanishing point priors, DenseVP and MotionVP. Firstly, we introduce DenseVP, a VP-guided scale-adaptive partition method for VSS, which extracts more fine-grained features for hard samples in the vanishing point region. Specifically, we apply dense partition strategy in feature blocks around the vanishing point, and then use cross-attention operation to enhance weak dynamic features in distant regions around the vanishing point. Moreover, we assume that the relative moving direction of the targets are along the line connecting the target and the vanishing point in common driving scenes. In this case, we try to employ vanishing point guided motion estimation to establish explicit correspondences across frames and have attained to the most relevant features from neighboring frames. Specifically, we sample forward and backward along the line connecting the VP and the target to find corresponding feature blocks, and use another multi-head cross-attention to fuse the dynamic temporal information. We also propose the vanishing point embedding technique, where vanishing point positions are embedded as a vanishing point-centered pseudo depth map, guiding the model to automatically attend to the most distant regions where targets appear at smaller scales. This is the whole pipeline of our method. In the MotionVP module, video frames are downsampled to extract context features, which go through cross-attention to capture dynamic context. It is further augmented by DenseVP to mine more fine features in the VP region through a two-scale partition strategy. In the upper part, we obtain local context and local details from downsampled and high-resolution target frames, respectively. In CMA, augmented dynamic context interacts with local context to generate the detailed tension map, guiding its merging with high-resolution local details for the final prediction. These are the quantitative results of our method on two popular benchmarks, ACDC and Cityscapes. And this is the qualitative comparison on ACDC. Finally, I want to summarize the contributions of our proposed VPSeg. First, we propose MotionVP, VP-guided motion estimation strategy for VSS. It's useful in high-speed scenarios in driving scenes with large motion. Second, we present DenseVP, the VP-guided scale-adaptive partition method for VSS. Third, we design VPSeg, an efficient context detail framework for VSS. Thank you for listening.